February 11th, 1893, Indian Head Proving Ground, Maryland. Captain William Sampson stands behind a reinforced observation bunker as ordnance experts, naval officers, and steel manufacturers gather in the frigid morning air. 300 yards downrange, a 6-inch nickel steel plate gleams in the winter sun, the latest attempt to protect America's warships from the increasingly devastating naval guns of the 1890s. The statistics are damning. In recent trials, conventional armor plates shatter like glass. Compound armor, steel backed with wrought iron, fails 40% of the time against modern armor-piercing shells. American battleships are becoming floating coffins. Britain's Royal Navy is pulling ahead. Germany's Krupp Works is developing something better. The United States is losing the naval arms race. Sampson signals the gun crew. The 6-inch rifled cannon roars. The 100-pound projectile screams downrange at 2,000 feet per second, enough kinetic energy to punch through any armor plate ever manufactured. The impact sounds like a thunderclap. Smoke obscures the target. When the air clears, ordnance officers rush forward with measuring instruments. The projectile has barely dented the surface. They fire again and again. 3 direct hits at point-blank range. The plate remains intact. No penetration, no cracking, no spalling that would kill the crew inside. Impossible, mutters a Carnegie Steel representative, lowering his binoculars. What these military experts don't know, what nobody in that frozen proving ground understands, is that the man who created this revolutionary armor isn't a metallurgist. He has no formal training in material science. He never attended university. He's a 68-year-old inventor who spent the last 40 years manufacturing screws. Hayward Augustus Harvey built his revolutionary armor plate using a technique so dangerous, so counterintuitive, that every expert in the steel industry had dismissed it as suicidal. He kept steel plates buried in charcoal at temperatures exceeding 2,200 degrees Fahrenheit for 2 to 3 weeks straight. One miscalculation meant explosions that could level a factory. One temperature variation meant worthless, brittle plates that would crack in combat. But on this February morning at Indian Head, Harvey's suicidal process just passed the most rigorous test in naval history. His plates are 15 to 20% stronger than anything else in existence. They will protect every major battleship built in America for the next decade. This is the story of how one blacksmith's hammer technique changed naval warfare forever. The 1880s. The world's navies are locked in an arms race that makes the Cold War look tame. Every major power, Britain, France, Germany, Russia, the United States, is pouring millions into battleships. These floating fortresses carry guns that fire shells weighing half a ton at speeds that can punch through solid iron. But there's a problem. Armor can't keep up with ammunition. Traditional iron plates are useless. A 6-inch shell tears through them like paper. Engineers try compound armor, steel faces backed with wrought iron, but it shatters under sustained fire. Ships take one hit, and crews die from spalling, shards of metal exploding inward like shrapnel grenades. The U.S. Navy watches helplessly as American sailors train on warships that can't survive a real naval battle. Between 1885 and 1890, the Navy commissions USS Texas, USS Maine, and 3 Indiana-class battleships, all with armor that fails 40% of ballistic tests. Secretary of the Navy, Benjamin Tracy, knows the truth. America's fleet is obsolete before it launches. We are building ships that will sink in the first engagement, he tells Congress in 1890. We need better armor, or we need to stop building battleships. The steel industry offers no solutions. Carnegie Steel Company's metallurgists experiment with nickel-steel alloys. Better than iron, yes, but not good enough. Plates still crack. Tests at Bethlehem Steel show 35% failure rates. The scientific consensus is clear. There's a fundamental limit to how strong you can make steel plate. Go harder, and it becomes brittle. Stay soft, and shells punch through. It's a metallurgical catch-22. By 1890, other nations are pulling ahead. France develops nickel-chrome steel that's marginally better. Germany's Krupp works experiments with surface treatments. Britain's Royal Navy orders compound armor from Sheffield, accepting the high failure rates because there's nothing better available. The U.S. Navy issues an urgent request. Any company, any inventor, any process that can produce armor plate superior to existing standards will receive massive government contracts. Bethlehem Steel, Carnegie, and Midvale Steel all submit proposals. The Navy tests them all. Nothing works well enough. Here's what experts know in 1890. Steel gets harder when you add carbon. But carbon makes it brittle. If you heat treat the entire plate to achieve hardness, it shatters under impact. If you keep it soft to prevent shattering, shells penetrate. What the Navy needs is impossible: a plate with a rock-hard face to resist penetration and a flexible core to absorb impact without shattering. Every metallurgist agrees it can't be done with existing technology. The stakes couldn't be higher. In 1890, a single battleship costs $6 million, more than $200 million in today's dollars. Without better armor, that investment is worthless. Worse, American sailors will die. Naval experts predict that in the next war, whichever nation has superior armor will control the seas. And right now, America is losing. This is where our story begins. Not in a university laboratory or a corporate research facility, but in a small workshop in Orange, New Jersey, where a 66-year-old inventor is about to discover something that will make him famous and change naval history. But first, you need to understand why nobody, not the Navy, not Carnegie Steel, not the greatest metallurgists in America, believes this old screw manufacturer has any business experimenting with armor plate. Hayward Augustus Harvey has no credentials. Born January 17, 1824, in Jamestown, New York, Harvey never attended college. No engineering degree, no formal training in metallurgy. His father runs a screw company, so young Hayward learns to be a draftsman. That's it. That's his education. But Harvey has one gift. He can't stop inventing. By 1865, he's founded Continental Screw Company, makes industrial bolts, screws, mundane hardware. But Harvey isn't content with ordinary products. He invents a peripheral grip bolt that revolutionizes industrial fasteners. He develops rolled threads that make screws 40% stronger and 60% cheaper to manufacture. By 1887, American Screw Company buys him out for a fortune. Harvey retires at 63. Most men would buy a country estate and play golf, not Harvey. In 1886, he establishes Harvey Steel Company in Orange, New Jersey, a modest workshop where he tinkers with steel, experimenting with razor blades, safe reinforcement plates, and industrial dies. He holds 125 patents. His neighbors think he's eccentric. His family thinks he works too hard. Then, in late 1889, Harvey reads about the Navy's armor crisis. He has no experience with armor, no background in ballistics, no reason to think he can solve a problem that's stumping the best metallurgists at Carnegie and Bethlehem Steel. But Harvey has been working with case hardening for years, a blacksmith's technique where you pack steel in charcoal and heat it to absorb carbon into the surface. Blacksmiths use it for tool edges, small parts. Nobody's ever tried it on massive armor plates because conventional wisdom says it's impossible to control the process at that scale. Harvey thinks differently. Late one night in his Orange workshop, Harvey stares at a 6-inch steel plate. He's been reading about medieval armor. How blacksmiths created hard edges on soft cores. The principle is simple. If you can drive carbon deep into the face of the plate, but keep the interior soft, you get both hardness and flexibility. The challenge is temperature control. Hold the plate at 2,200 degrees Fahrenheit for weeks, long enough for carbon to penetrate deep into the steel. Too hot, and the plate warps. Too cool, and carbon doesn't penetrate. Any variation in the charcoal bed creates weak spots that will crack under fire. Every metallurgist Harvey consults tells him it's impossible. You'll never maintain consistent temperature for 3 weeks, they say. The plate will warp, the factory will burn down. Even if it works once, you can't scale it to production. But Harvey isn't a metallurgist. He's a screw manufacturer who spent 40 years perfecting industrial processes. He knows how to control temperatures. He knows how to scale production. He knows how to turn a lab experiment into a factory operation. In January 1890, Harvey builds a custom furnace in his workshop. He packs a nickel steel plate in finely divided charcoal. He heats it to 2,200 degrees Fahrenheit, and then he waits for 3 weeks. His sons think he's lost his mind. Harvey's workshop, March 1890. The furnace has been running non-stop for 21 days. Harvey monitors temperature gauges every 4 hours, adjusting gas flow to maintain exactly 2,200 degrees Fahrenheit. One spike could ruin the plate. One drop could render the entire experiment worthless. His workers are terrified. Keeping charcoal at that temperature for weeks is inherently dangerous. Gas leaks, structural failures, the entire building could go up in flames. "This is insane," his chief foreman tells him. "You're going to kill somebody." Harvey doesn't listen. On day 22, he begins the most dangerous phase, quenching. The superheated plate must be rapidly cooled to lock the carbon into the steel's crystalline structure. But dropping a 2,200 degree plate into oil creates violent thermal shocks. If the plate shatters, it becomes a fragmentation bomb. Harvey clears the workshop. Only he and 2 volunteers remain. They lift the glowing plate with tongs and plunge it into oil. The workshop explodes with smoke and flame. The oil ignites. For 30 seconds, Harvey can't see anything. When the smoke clears, the plate sits at the bottom of the quenching tank, intact. But Harvey knows this means nothing. Dozens of metallurgists have created hard steel plates. The question is, will it hold up under fire without shattering? He needs to test it, but there's a problem. Ballistic testing requires naval ordnance. Guns Harvey doesn't have access to. Government proving grounds won't test unproven armor from an unknown inventor. Carnegie Steel and Bethlehem control all the test facilities. So Harvey does something audacious. He contacts the French armor plate company Schneider and SUICIDAL. He ships them an experimental 10.5-inch plate and asks them to test it against their best armor. If Harvey's plate performs better, Schneider will lose contracts. They have every reason to refuse, but scientific curiosity wins. In January 1891, Schneider conducts trials. They fire armor-piercing shells at Harvey's plate and their own compound armor side by side. The results shock everyone. Harvey's plate resists penetration better than anything Schneider has ever manufactured, not by a small margin, by 15–20%. The charcoal carbonized face is harder than steel ever tested, yet the soft nickel steel core absorbs impact without cracking. It's exactly what the Navy said was impossible. Schneider sends the data to Harvey with a note. "We don't understand how you achieved this, but your process works." Harvey immediately contacts the U.S. Navy. They respond with skepticism. Secretary Tracy's metallurgical advisors review Harvey's data and conclude it's either fabricated or a fluke. "Surface carburization cannot be controlled at this scale," one expert writes. Mr. Harvey's claims violate fundamental principles of metallurgy. The Navy's chief metallurgist, Commander George Converse, is more blunt. That process is illegal under the laws of physics. But Tracy agrees to one test. Just one. If Harvey's armor fails at Indian Head Proving Ground, his company will be blacklisted. If it succeeds, the Navy will consider limited production trials. Harvey accepts. He knows he's risking everything. September 1891, Washington Navy Yard. Hayward Harvey stands in a conference room facing 15 of the most powerful men in American industry. Representatives from Carnegie Steel, Bethlehem Steel, and Midvale Steel, companies with factories the size of cities, government contracts worth millions, and metallurgists with degrees from Yale and MIT. Harvey is a 67-year-old screw manufacturer with no formal credentials. Captain Sampson opens the meeting. Mr. Harvey claims he can produce armor plate 15–20% superior to current standards using surface carburization. Carnegie's experts have reviewed his process and concluded it's unworkable at production scale. A Carnegie metallurgist stands. Mr. Harvey's laboratory results are interesting, but they're irrelevant. Maintaining 2,200-degree temperatures for 3 weeks requires perfect heat control across the entire plate surface. Any variation creates weak spots. In a production facility producing dozens of plates simultaneously, this level of precision is impossible. Furthermore, adds a Bethlehem representative, even if the process works, it's economically unviable. 3 weeks per plate? The Navy needs thousands of tons of armor. Harvey's process can't scale. The room erupts in agreement. This is the expert consensus. Harvey Steel Company is too small. The process is too dangerous. The whole thing is too impractical. Then Harvey speaks. Gentlemen, you're correct that I lack your credentials. I'm not a university-trained metallurgist, but I've spent 40 years controlling industrial heat treatment processes at scale. Rolling screw threads taught me precision. Manufacturing safe plates taught me quality control. I know how to turn an experiment into production. He places test results on the table. Schneider tested my plates in France. They outperformed compound armor by 20%. The Washington Navy Yard tempered a Schneider plate using my process and tested it at Indian Head. It survived 3 direct hits without penetration. Laboratory conditions, interrupts a Carnegie engineer. Then test it again, Harvey replies. Give me your hardest test. I'll produce 3 plates using my process. Carnegie and Bethlehem produce 3 plates using your best methods. We fire at all 6 under identical conditions. The data decides. The room goes silent. Harvey is calling their bluff. Captain Sampson leans forward. Mr. Harvey, if your plates fail this test, you understand your company will lose all Navy contracts? I understand. And you're willing to stake your reputation on this? I am. The Carnegie representative stands. Captain Sampson, this is a waste of naval resources. We're entertaining proposals from a screw manufacturer while serious companies are developing real solutions. Then you should have no trouble outperforming him, Sampson replies coolly. Secretary Tracy intervenes. Gentlemen, we're not in the business of protecting corporate interests. We're in the business of protecting American sailors. If Mr. Harvey's process works, I don't care if he learned metallurgy from a blacksmith. We're conducting comparative trials. If you're learning about innovations that changed history, make sure you're subscribed so you don't miss our next episode. We've got an incredible story coming about the engineer who designed the most devastating weapon of World War II and tried to stop it from being built. Hit that subscribe button now. January 1892. Bethlehem Iron Company. 3 10.5-inch plates arrive from Harvey Steel Company. Bethlehem metallurgists inspect them skeptically. Carnegie submits 3 compound armor plates. Bethlehem submits 3 nickel steel plates. All 9 plates undergo identical ballistic testing at Indian Head over 6 months. The results are unambiguous. Harvey plates, 0% failure rate, no penetrations, no cracking, no spalling. Carnegie plates, 35% failure rate, 2 plates crack after repeated impacts. Bethlehem plates, 28% failure rate, 1 plate suffers catastrophic spalling. In October 1892, the Navy's Bureau of Ordnance releases findings. Harvey armor demonstrates 15–20% superior ballistic resistance compared to all tested alternatives. The Harvey process is recommended for immediate production licensing. The steel industry is stunned. Within months, Carnegie Steel and Bethlehem Steel both negotiate licenses to use Harvey's process. By 1893, every major steel manufacturer in America is producing Harveyized armor. The Navy orders thousands of tons for USS Texas, USS Indiana, USS Massachusetts, and USS Oregon. Hayward Augustus Harvey, the screw manufacturer with no credentials, has just revolutionized naval warfare. But the real test isn't in proving grounds. It's coming in combat. February 11, 1893, Indian Head Proving Ground. We return to that frozen February morning where our story began. Captain Sampson is about to conduct the most important armor test in naval history. Not a laboratory experiment, but a full-scale battlefield simulation. The target, a 14-inch Harvey armor plate manufactured by Bethlehem Steel, the thickest ever produced. The projectile, a new armor-piercing shell designed specifically to defeat face-hardened armor. The stakes, America's entire battleship program. Naval experts from Britain, Germany, Russia, and France are watching. If Harvey armor fails today, those nations will dismiss the process as American propaganda. If it succeeds, every major navy in the world will demand Harveyized plates. Sampson orders the first shot. Range, 300 yards. Striking velocity, 2,000 feet per second. Impact energy, enough to punch through 3 feet of solid iron. The shell hits dead center. The impact sounds like a cathedral bell. Observers rush forward. The Harvey plate shows a shallow depression, less than 2 inches deep. No penetration, no cracks. The shell shattered on impact. Second shot, same result. Third shot, the plate remains intact. British naval observers telegraph London immediately. Within weeks, the Royal Navy begins licensing Harvey's process. Russia's Imperial Navy orders Harveyized plates for 3 battleships. Germany's Krupp Works studies the technique and develops improvements, but they're building on Harvey's foundation. By 1895, Harvey armor is the global standard, but the ultimate test comes during wartime. April 23, 1898, Santiago Harbor, Cuba. The Spanish-American War erupts. The USS Oregon, USS Indiana, and USS Massachusetts, all protected by Harvey armor, engage Spanish cruisers equipped with older compound armor. Commander Charles Clark commands USS Oregon as Spanish shells slam into her hull. Direct hits at close range. The kind of impacts that would have sunk American warships 10 years earlier. But Oregon's Harvey plates hold. No penetrations. Minimal damage. American gunners keep firing. The battle lasts 3 hours. USS Oregon takes 17 direct hits. 0 casualties from armor penetration. Spanish ships, with inferior armor, suffer catastrophic damage. Crews die from spalling and internal explosions. When the smoke clears, the Spanish fleet is destroyed. American ships are battered but operational. Naval historians later conclude, Harvey armor decided the Battle of Santiago. Without it, American casualties would have been catastrophic. 1905, Battle of Tsushima Strait. The Russo-Japanese War provides the definitive test. Russian battleships equipped with Harvey armor engage Japanese vessels at long range. Both sides use modern armor-piercing shells. Russian battleship Rostislav, protected by Harvey plates ordered from American manufacturers, survives repeated hits during a 4-hour engagement. Post-battle analysis shows her Harvey armor prevented 23 penetrations that would have sunk older ships. Japanese Admiral Togo Heihachiro later writes, "The Russians' American armor proved more effective than anticipated. Had their gunnery matched their protection, the battle outcome might have differed." 1914-1918, World War I. Harvey armor protects Allied battleships at Jutland, the largest naval engagement in history. British dreadnoughts HMS Iron Duke and HMS Warspite, both with Harvey process armor, survive sustained German fire. German gunnery officer Friedrich Ruge records in his memoirs, "We scored direct hits on British battleships that should have been catastrophic. Their armor absorbed punishment we thought impossible. We later learned the British were using American face-hardening techniques that made their plates far superior to our expectations." By 1916, Germany's Krupp Works has developed improvements on Harvey's process, adding chromium to create even harder faces through gaseous carburization. This Krupp cemented armor becomes the new standard. But Krupp's engineers acknowledge their process builds directly on Harvey's innovation. As metallurgist Rudolf Maurer writes in 1917, Harvey's genius was recognizing that carburization depth, not overall hardness, determines ballistic resistance. We merely refined his discovery. 1945, end of World War II. By the war's end, armor technology has evolved far beyond Harvey's original process. Rolled homogeneous armor, composite ceramics, and reactive armor dominate. But naval historians note, every face-hardened armor system used in WWII, American, British, German, Japanese, descends from Harvey's 1890 breakthrough. The USS Texas, commissioned in 1914 with Harvey armor, serves in both world wars. She bombards beaches at Normandy in 1944, 54 years after Harvey's first experiment. Her armor, now obsolete against modern shells, still protects her crew from near misses and fragments. Captain Baker of USS Texas writes after D-Day, "Our old girl took hits that would have sunk ships from grandfather's era. Harvey armor, even outdated, kept us in the fight." Production numbers. Between 1891 and 1905, American steel companies produce over 45,000 tons of Harvey armor for U.S. Navy battleships. Licensing agreements with Britain, France, Russia, and Japan generate millions in royalties for Harvey Steel Company. By 1900, 73% of all battleship armor worldwide uses Harvey's process or derivatives. USS Indiana-class battleships alone carry 9,000 tons of Harvey plate each. Without this armor, naval experts estimate American casualties in the Spanish-American War would have tripled. Lives saved. While impossible to calculate precisely, naval historians estimate Harvey armor prevented thousands of deaths during the Spanish-American War, Russo-Japanese War, and World War I. At Jutland alone, British ships with Harvey process armor survived hits that would have sunk earlier vessels, saving an estimated 3,000 sailors. The story of how one inventor's obsession saved thousands of lives is just one of many untold stories of military innovation. If you haven't already, hit that like button to help others discover these forgotten heroes. And check out our episode on the radar engineer who detected Pearl Harbor 50 minutes before the attack and was ignored. August 28, 1893, Orange, New Jersey. Hayward Augustus. Harvey dies at home age 69. Just 6 months after his armor triumphed at Indian Head, he never sees his plates used in combat, never witnesses the Battle of Santiago, never knows his process will protect battleships for half a century. His obituary in the New York Times is 14 sentences. Most of it discusses his screw patents. The armor innovation gets 2 lines. Harvey never sought fame. When the Navy offered to name a battleship after him, he declined. When Carnegie Steel proposed a ceremonial position as chief consulting metallurgist, he refused. He returned to his orange workshop and continued inventing until weeks before his death. His son, Hayward Harvey Jr., takes over Harvey Steel Company and manages licensing agreements, but the elder Harvey remains enigmatic. He published no scientific papers, gave no lectures, filed detailed patents, but never explained his reasoning publicly. Metallurgists spend decades analyzing Harvey's process, trying to understand how a screw manufacturer with no formal training achieved what trained experts couldn't. The answer appears to be obsessive empiricism. Harvey conducted thousands of experiments, meticulously documenting temperature, timing, and carbon content until he found the precise combination that worked. Harvey didn't understand the science, writes metallurgist Robert Hadfield in 1910. He simply understood steel in a way theorists didn't. He had a blacksmith's intuition combined with an industrialist's precision. Modern legacy. Harvey's fundamental insight that carburization depth matters more than overall hardness remains valid today. Modern case-hardened steel for gears, bearings, and cutting tools still uses variations of Harvey's process. Tank armor evolved beyond face hardening, but the principle of hard faces over tough cores persists in composite armor. Modern chobham armor, ceramic plates, and reactive armor all separate hardness and toughness into distinct layers, exactly what Harvey pioneered in 1890. In 1975, the American Society for Metals posthumously inducted Hayward Augustus Harvey into the Metallurgical Hall of Fame, recognizing his process as one of the foundational innovations in materials science. The citation reads, "Despite lacking formal training, Harvey revolutionized armor protection through systematic experimentation and industrial-scale innovation. His work saved countless lives and demonstrated that practical engineering insight can achieve breakthroughs theoretical science cannot predict." The moral lesson. Hayward Harvey's story challenges everything we believe about expertise. He had no credentials, no formal education, no theoretical framework. Every expert in the steel industry dismissed him. But Harvey had something more valuable than credentials. He had experience, obsessive attention to detail, and willingness to ignore expert consensus when his experiments proved otherwise. The Navy's experts said surface carburization couldn't be controlled at scale. Harvey proved it could. Carnegie's metallurgists said the process wouldn't work in production. Harvey proved it would. The scientific establishment said his success violated metallurgical principles. Harvey didn't care what the principles said, he cared what the data showed. In an age that worships academic credentials and expert consensus, Harvey's story is a reminder. Sometimes the most revolutionary innovations come from people willing to try what experts insist is impossible. Because Harvey didn't know it was impossible, he did it anyway. And thousands of sailors came home because of that.